on the go. So just to remind ourselves, aldehydes, they have the carbonyl group on the end of the chain. So they always have that group there. So for example, this would be ethanal. You obviously don't need to call it ethan 1-al because it can only go on the end. This would be propanol, propanal, and so on. If you look at ketones, the carbonyl's got to be in the middle of the chain. So the simplest ketone, you can't have one with just 2 carbons. The simplest ketone has got to be with 3 carbons. So that would be propanone. Again, we don't need any numbers there because you can't have, if it was propan 1-one, it would be propanal. It can only go on carbon number 2. But when you get them a little bit bigger, then you obviously, if you had that, you would have to call that pentan 3-one, and of course you could have an isomer of that pentan 2-one where it was on the second carbon along. Okay, so the important thing about these is because the oxygen is electronegative, you have a delta positive carbon on the carbonyl, and that means that nucleophiles are going to be attracted towards that. Okay. Now the 2 nucleophiles we need to know about that react with these are, first of all, on the hydride ion, which is hydrogen with an extra electron. This don't really come across that very frequently because, of course, hydrogen is very small. So you stick an extra electron onto a hydrogen atom. The charge density of the hydride ion is going to be pretty high, which means it's not that stable. And the other one, which we've come across before as a nucleophile, is the cyanide ion. Cn minus. Okay, just to remind ourselves, well, you have a triple bond to the nitrogen. 3 of the carbon electrons are in the triple bond. There's the other electron from carbon, and this electron, this blue electron is come from somewhere else, like so you have potassium cyanide or whatever. That's your negatively charged cyanide ion. So right, let's have a look at the mechanism with, first of all, let's look at the hydride ion, how that reacts with ethanal. Okay, so we have, here's ethanol. And here is our nucleophile, the hydride ion. It's got a lone pair, negatively charged. And of course, this carbon is delta positive. So the first step in the mechanism is that lone pair is going to form, oops, that lone pair is going to form should be a double-headed arrow there to that carbon. That carbon is now going to be forming 5 bonds. So of course the one of the bonds here is going to break, and it's the pi bond. That goes into the oxygen. So let's draw what the intermediate is going to look like there. So nothing's happened to the methyl group. We've got our red hydrogen attached. This is the original hydrogen that was there already. And there we've got O. Now that, well, it's got to have a negative charge on it because this was the ethanal was neutral. and the hydride ion was negatively charged, so that means there's got to be a negative charge on that somewhere, and the negative charge is of course on the oxygen. Okay, now I'm going to put a lone pair there. There's actually 3 lone pairs really on the oxygen. This is going to be a very strong base. That means it's very good at accepting protons. So it will take a proton off the solvent. We don't have to actually show that. We can just write it down as H+. So if I write down H+ here, and what's going to happen is that pair of electrons is going to go and form a bond to that. And so we can see that the final product is going to be the alcohol. Okay, right. So I should really put those in the proper colors. So let's say that that's the red hydrogen. And this hydrogen here has been picked up from the solvent. That's the green one. So we can see that what we've done there, we have turned an aldehyde into a primary alcohol. And you probably remember the reverse of that reaction. A primary alcohol turning into an aldehyde, that's an oxidation. So this is a reduction. And the reducing agent is the hydride ion. Just incidentally, the oxidation number of hydrogen in the hydride ion is -1. It's not +1. Okay, so you can see the hydrogen has gone from -1 oxidation state to a +1 oxidation state. So that the hydride ion has been oxidized. It's a reduction reaction. Okay, so that is the hydride ion reacting with ethanol. Let's see what would happen with propanone. So exactly the same mechanism, right? So CH3. Here is our hydride ion. So that's going to attack that carbon there. The pi bond breaks. We've now got a negative charge on the oxygen. Got our new hydrogen attached there. And this is then going to pick up a proton from the solvent. So just drawing one of the 3 lone pairs on the oxygen there, and that's going to go onto there. And we're going to end up with a secondary alcohol as the product. So we've gone from, if you reduce a ketone with, it goes to a secondary alcohol. And we've come across to reverse that reaction before, where we oxidize a secondary alcohol to a ketone using potassium dichromate. Right, that is the reaction of the carbonyls with the hydride ion. Now, the hydride ion, we need to talk a little bit about what is the reagent for this reaction. The hydride ion right, that's provided by sodium borohydride, NaBH4. That's the reagent. So if you wanted to write down not the mechanism, but just the reagents and conditions, you'd have CH3 aldehyde going to the primary alcohol, and the reagent you would need is sodium borohydride in ethanol. Right, that's got to be in ethanol, not in water, because hydride ion is such a good reducing agent. It will reduce the hydrogens in water to hydrogen gas, so it's got to be in ethanol. Right, let's just have a little think about sodium borohydride. So NaBH4. Well, we know sodium always forms ionic compounds, so we know that's got to be an Na plus ion. So that means this BH4 bit has got to be a negatively charged ion. Boron is in group 3 of the periodic table, so let's have a think about, so we've got a boron there, and these are hydrogens. So BH3 would have this formula, dot and a cross. Now, boron has it's only got 3 electrons in its outer shell, so you can see that that compound has only got 6. So it means it's, to make a full 8 outer shell, it's fairly willing to accept lone pairs of electrons. And if you get a hydride ion, so this is a hydride ion, it's got one of its electrons and then one that it's got from somewhere else. Okay, so this is going to form a dative bond here. So I said before that the H- ion would have a very high charge density. Oh, this thing, the BH4- ion, well, the negative charge is spread over a much bigger the boron atom and 3 other hydrogens, so that makes it more stable. So the hydride ion is provided as NaBH4. When you're drawing the mechanism, you don't have to draw how this BH4- ion is reacting. It's just okay just to write down the hydride ion reacting with the alcohol, with the carbonyl compound. But that is what the hydride ion is. Okay,